Hello, hello. Good afternoon, Amanda. Okay, hold. I lost my board again. Good afternoon, everybody. I mean, well, I will.
Good afternoon, Professor.
Oh, good afternoon, Caroline. All right, hold on. Good afternoon, board that I just lost. It's good to see Caroline. It's good to hear, see Amanda. It is good to read Mackenzie. I'm going out of order because I'm trying to get my board back. Sorry, but hello. Come on. Okay, there we go. And there's Kevin. Hello. Good afternoon, Rashman. Awesome. Okay, wait, sorry. Wait, yes. Good afternoon, Caroline. Good afternoon, Amanda. Good afternoon, Caitlin, Evan, Kevin, Amy, chat. Oh, and more people are coming. Good afternoon. Good afternoon, Amanda. Good afternoon, Caitlin. Good afternoon, Kevin. Good afternoon, Amy. C. Good afternoon, Evan. Good afternoon, Stephen. Good afternoon, Mackenzie. Good afternoon. Oh, my board again. Why is it? Maybe it's because it's. Hold on. Okay. Good afternoon, Samaya. Hello, Kirsten. Oh, that's interesting. Hello. Right. Good afternoon. That sounds familiar. Good afternoon, Rashman. Hello, Estrella. Good afternoon, Jose. Okay. All right. Let's get rolling here. The board is back. Let's see if I can keep the board for 2 minutes. All right. Oh, and more people coming. Okay. Okay, I'm getting all confused here, but oh, hi, you've been okay. Excellent. Oh, good afternoon, Adan. All right, awesome. Okay, let's do some physics. Yes. Okay, let's do some. We are going to continue. Yeah, let's just get. Okay. Oh, thank you. Okay, I see direct chat. I think. Oh, thank you. Okay, understood. Direct chat. There goes the board again. Why is happening so much right now? Sorry, maybe because it's plugged in. Is that possible? Right, hold on. Okay. We're going to pick up right. Well, all right. These equations on the board is what I want to get to. That's our next goal. They look very similar to equations that we just established. I mean, they certainly have integrals in them. They're similar, but we have not established these equations yet. They are my next goal. To be honest, I don't think they're my next goal, these equations. So you can write them down, but don't think we've gotten to them yet. And ideally, I want to get to them by the end of this class, but I actually don't think we'll get just almost to them, but I'm going to get rolling now in the hope that I can. So, all right. So what we are still in, here we are. We are still in the context of homework 1B here. We are particularly backing up and looking at the mathematical underpinnings and background and concepts that underlie, in particular, questions 4 and 5. Which again, you have answers to, but now we're really trying to unpack like what's going on behind question 4 and 5. I also want to say again, like I'm very happy to say that I've received many homework ones. I received a number of revisions. I even received some third drafts from people. And every time any one of you like submits another draft or an update, you get more and more points. And I'm trying to. Well, anyway, but even if you haven't yet at all submitted it, you still could get the points. Homework 2, same thing. The people that have already submitted some drafts for homework 2 have gotten a lot of points. They haven't gotten all the points yet, unless they literally did all of it. but every time they submit, every time those of you, and there's about 4 or 5 of you who have submitted homework 2, you got a bunch of points just for the fact that you tried and you submitted it early or, on time. You can keep submitting for more points. All of you may have noticed that I'm trying to get the points back to you faster, maybe than last semester. Right now, it's a little bit at the cost of extensive feedback. I'm sort of favoring points over extensive feedback now, especially because I'm spending so much class time actually talking about the homework questions. So I'm sort of trying to strike a balance where every time you give me another draft or another attempt or progress, I'm certainly reading what you're doing and I'm noting the progress and I'm seeing how you're improving. I'm not giving a lot of feedback right now because hopefully you're getting the content in class. And I want you to see that the faster you get stuff to me, the faster you revise and update, the faster you'll get points back. That's my compromise for right now. So keep them coming. Again, everything you give me is a draft that is subject to improvement later. And same thing with the points. Every time you get points from me, don't think of it as a final score. Think of it as that's how many points you've accumulated so far. There goes the board again. I think you get it. But what I'm really saying is partly I'm trying to acknowledge that, believe me, I'm reading your work, but I'm not giving a lot of detailed feedback on it now. I know that. I'm trying to give you points for it. But similarly, don't think when you get points, it's not a final score. It's not the door's not closed on anything. Just the faster and the more you get stuff to me, the more points you get. So also note, there will be a homework 3 soon, but there isn't yet. There's still plenty of time to do homework 2 and even homework 1 because we're still talking about them both in class. All right, hopefully that's clear to people. Just so you just keep doing stuff, I'll just keep giving points. It's like that, but I got to get the board. So right now, anyway, all of that is to say, this board. All of this is to say that we're talking about the material of homework 1. We're talking about where I got my answers to questions 4 and 5. The last thing we said, I believe, last week was we established that work, the physics concept, is defined to be the path integral of force. So the work done from, a little correction here. The work done from one location, call it x1, to another location, call it x2, is the integral of the dot product of force with every little bit of displacement that we travel from x1 to x2. Okay, so we established that work is an integral, which means that if we had a way of computing the continuous sum of infinitesimal little products from x1 to x2, if we had a way of computing this continuous sum, then we would have computed the physical work done from x1 to x2. In and of itself, to say that is a lot. Like, hopefully that tells us something about what an integral is. Hopefully it tells us something about what a dot product is. Hopefully it tells us something about what the physical concept of work is. But it does not, let me please repeat, all of the discussion that we've said for the last 2 days about integrals and work and dot products, all of that says what they mean and why they arise and why we care about them. None of it says anything about how you compute an integral. It doesn't. So then we went on and we used our notation and our knowledge of differentials to realize this thing called the fundamental theorem of calculus, to realize this observation called the fundamental theorem of calculus, which says that the integral of a derivative of a function actually is the original function evaluated at its boundaries, or in other words, the definite integral of the derivative of a function is the value of that function at the limits of integration. What that means in English is that what it means in English is that the integral turns out to be the derivative in reverse. Now, I cannot emphasize enough, even though I know this has been emphasized a lot in your prior lives in math classes, I want to emphasize that it was emphasized a lot in my prior life as a student in math classes. And every time it was emphasized in a certain kind of way at a certain time in my life, it went straight over my head. Or in fact, sometimes it went into my head and bounced off in a way that really annoyed me and made me hate math more at the time. What I'm saying is, to me, every time I heard the fundamental theorem of calculus, every time I heard that in order to do an integral, you do a derivative backwards, I thought, duh, not because I understood integrals or derivatives, mind you, not at all. I thought, duh, because I thought that what they had already taught me was that an integral was an antiderivative. I thought that the first time I ever saw an integral, it was presented to me as an antiderivative. So, and I'm not sure if that's actually true or not. I'm not sure if that's what they said, but that is what I heard. I thought that what an integral was an antiderivative. So when they finally got to this theorem that they called fundamental, and they made a really big stink about it and said, guess what? It's really fundamental to realize that the integral is the inverse function of the derivative. I was like, duh. Haven't you been saying the whole time that the integral is the antiderivative? Of course, the antiderivative is the antiderivative. Like, why is this a revelation? And so then anytime they tried to do anything with it, unconsciously or not, hostilely or not, I just tuned out because I was like, this is just more math mumbo jumbo. This is just more people thinking something is exciting that doesn't make any sense. So I'm just going to accept and memorize and move on and try to do okay, but I'm not going to actually take any of this seriously. By the way, again, I'm not saying I consciously thought any of that or much of it, but I am saying I never understood why it was a big deal and so fundamental to say that the integral was the antiderivative when I thought the whole time the definition of the integral was the antiderivative. What I'm here to tell you is it was my misunderstanding, and it might have been the way they presented it. I don't know, but it was my misunderstanding. The integral by definition is not the antiderivative. The integral by definition is the continuous sum of products. If you want to think in terms of graphs, the integral is the area under the curve. That has, in and of itself, has nothing to do with tangent lines or slopes or anything else. It has to do with the effect of a function over some region. In this case, some region of space. It turns out that and that's why the integral is useful, because it's the continuous sum. It's the continuous accumulated effect of some function over the space of that function. So in physics terms, the integral of force means what the force is actually accomplishing as it pushes or pulls throughout some long space. That's what, sorry. Someone after this whole class is going to have to explain to me how to get the focus do not disturb thing to work on my phone, because I feel like I keep telling it to not disturb me, and all it does is disturb me. I mean, I understand that with my 8-year-old son, but an electronic device really should listen. Okay. And then you're like, that's not your device's problem. That's your ADHD's problem. Yaverbaum. Okay, fair enough. Touche. Light bulb, lizard, distraction, voices in head, integral. Okay, I'm saying the integral of force means the accumulated effect, like the accomplishment of a force as it acts throughout some measurable region of space. That's what, like the continuous sum of the force times how much space it's acting through. That's what integral means. That's why I want it. I want to know what's a force accomplishing as it pushes or pulls throughout some space. I think that's a reasonable question for a physicist to ask. But that doesn't tell me how to get the answer. That's just notation that says the integral is the accumulated effect of the force throughout some displacement. How the heck do I do the limit as delta x approaches 0 of the sum of a bunch of delta x's dotted with a bunch of f's. How do I do that? I don't know. But it turns out what we showed last time, or what it says very quickly in black on the bottom of this page, it turns out that the integral of the derivative of some function is just the function itself. It turns out that when you take the continuous sum of products of some function, what you're doing is taking the slope of the tangent line to that function in reverse. I didn't see that coming. When I put it that way, like, oh, that is a revelation. That's such a surprise. I would think it's like some weird like sidebar, but it's such an important revelation that we call it fundamental, because it means from now on, if you want to compute this continuous sum, all you got to do, if you can, when you can, is do derivatives backwards. I didn't see that coming when I put it that way. So the fundamental theorem of calculus is a double equal sign. It's not a triple equal sign. The definition of the integral is the continuous sum. The way to compute an integral, evidently, when we can, is to do a derivative backwards. So apparently we can calculate the work done by some function, assuming the function, we can calculate the work done by some force, assuming the force is a function of position in space. So we're going to do that. We're going to use our knowledge now of work and our knowledge of the fundamental theorem of calculus. We're going to calculate the work done by a spring in order to restore a mass from some position back to equilibrium. However, first, a word from our sponsor. This is not a side. I mean, this is not a tangent. This is like totally the material. In order for us to do that, I want to make sure we're sort of on top of some of our basics from Calc 1. Like I'm talking all about integrals here, which I know you did in Calc 1, but we're really getting deep into integrals here, I hope. But and I think integrals are tricky and interesting and warrant a lot of discussion. Derivatives, I'm thinking that many of you are a little bit more solid on, at least the basics of derivatives. So, and we need that to do, because we're going to do a derivative backwards. So we better make sure that we remember how to do it forwards. So I'm going to ask you right here on the board, I'm going to ask you to put in direct chat, please, when you get a chance, in direct chat. Let's make sure we're together, and you could submit for points for participation and all that. I mean, you should, in fact, in direct chat, just look at what's on the board here. Assume you've got some function, y equals a x to the n. In other words, x is the independent variable, n is a constant. Like it's like a number, like 1 or 2. It's a power, like so it's an integer, like 1 or 2 or 3 or whatever. And a is also some constant. It's just some number. It's a coefficient, also like 3 or 4 or 5 or whatever, or -7. Blah, blah, blah. So assuming that, oh God, I already put the answer on that. I'm so wow. I didn't mean to do that. That's funny. Well, I guess it's too late. All right. I'll give you something to do in a second, but I didn't mean to put the answer there. But whoa, and now that's, oh my God. Okay, no, you know what? I'm going to ask in direct chat, especially since I just messed it up, in direct chat, even though there's an example given right here, there's an example from what I'm looking for, right? I give an example, like if your function is y equals 5x to the 4th, I claim that the derivative of that would be like 20x to the 3rd, right? It's a little hard to read. That's like a refresher reminder. Hopefully that is not, hopefully to most of you, what I just wrote here at the bottom is like familiar and not surprising or confusing. But to make sure we're on the same page, can I ask you in direct chat, put that in general terms. I'm asking for the power rule in effect, in general terms. If you have a function y equals ax to the n, then what is its derivative written in terms of a's and x's and n's? Like what's the rule? Could you please put in the direct chat, and I will acknowledge once you've put it in, but I won't say if it's right or wrong. I mean, I'd like to get as many people responding as possible in the direct chat. Just tell me if some function is y equals ax to the n, then what's the derivative of that function written in terms. So where the highlight is right there. Can you please, and I'm getting nervous if no one puts anything in the direct chat. Please put in the, oh, there we go. All right. Awesome. Oh, here we go. Awesome. I'm seeing things in the direct chat. Awesome. In fact, everything that's in the direct chat so far is right, which is great. You're totally with me. That's great. I mean, if you want me to say your names, I mean, I certainly will. But no, and you should all submit this for class participation. Like, seriously, awesome. I'm seeing it. Awesome. Very close. Last person who just, very, very close. Hold 1 second. I'm just going to respond to that. I don't have time to respond to everybody, but hold on. Okay, I got a bunch of answers. I didn't hear from everybody, but I've heard. So, and everybody's definitely with me. Everybody who answered, even. And by the way, let me just remind you again, tactfully to all of you, every one of you just gave an answer. Like, close. Hold on a second. Hold on 1 second. So I want to say to all of you, remember, if you just put in an answer, remember, there's at least one portal besides the regular portal where you can double dip this. There's a portal that says like 4 right or 4 wrong, meaning if you put any answer to a question, whether it was right or wrong, you could put it in for points there. And then also, if you happen to have got an answer that I say is not exactly complete. Oh, good. Okay, good. Direct chat person. Good. If you got something that wasn't complete or wasn't fully right, remember, there is a special portal, not to be weird, but to everybody, there's a special portal specifically for answers that are not completely right or that are wrong, where you get extra points for being wrong. Like, literally, I don't know how to emphasize that enough. Like, I want to encourage you, so you can double dip. You can put this answer in the portal that just says for right or for wrong, and you can also put in the portal that says for wrong if you're wrong. And there's a reason for that. Don't be ashamed. In fact, the very reason is to encourage you all to not be ashamed of wrong answers. Okay, so just remember. So thank you all for participating in that. And so now I'm gonna. Oh, good. And there's another person who just participated. Good, exactly. So that's great. Yes, you're with me. Okay, and what the people have been putting in the chat, and you can keep doing it if you want. What everybody seems to be telling me is, in effect, the power rule. You're saying that if you've got some function that is what we would call an algebraic function, a coefficient times a variable raised to some power, then what we do is to take a derivative, we multiply the whole thing by the power, and then we lower the power by 1. So it becomes, it becomes right, the thing that was a n x all gets multiplied by n, so it becomes a n x, and then the n itself gets lowered by 1, right? So 5x to the 4th all gets multiplied by 4, so we get 20 times x to the, but then the 4 gets lowered to a 3, right? And it's a rule that comes straight from the definition of derivative. It doesn't seem like it does. It seems very arbitrary, but I might take a moment next week maybe to even show everybody why this rule makes sense. But it does. And so now, bearing that in mind, so remember that, right? So that's just how you take derivatives of algebraic functions. So now, bearing that in mind, so given all the above, what we're going to do now as a group is compute the work done by a spring of stiffness K. What is the work done? In order to restore a mass M from an initial position x naught back to equilibrium x equals 0, okay? So in other words, the whole issue of homework 1B, we've got this mass on a spring. It's sitting at some initial position, x naught. We let it go. The spring starts pulling on it, doing work on it, moving it through a space, displacing it from position x naught to position x equals 0. We want to know the total amount of work, the total accomplishment of this force as it acts throughout this entire finite measurable region of space, i.e. from x naught to 0. We want to know the total work done by the spring. Now, and that's what we're going to figure out. Now, let me just caution you for a moment. The variable here, the independent variable is x, right? X as in where the mass is. That is the independent variable. The dependent variable, in effect, is F, the force. Force depends on where the mass is. So those are the variables. Everything else here is a constant, like x naught, for example, is a constant, which really means to me, it's a number. In effect, x naught could be the number of 15 centimeters. Hi. X naught could be the number. Good to see you. Good to see you. X naught could be the number 15 centimeters as it is in the homework problem, right? But so I could write it as the number 15 centimeters, but because I'm trying to be a little bit more general, because I'm trying to acknowledge that 15 centimeters is just a measurement that was made one day by one lab group in the lab, and another lab group could have made a measurement of 17 centimeters, right? So to be general, to cover all the different cases, I'm calling it x naught, and we want to get used to that. But notice I'm calling it x naught. That's a specific number. I just don't know what it is. But it's not x. It's not a variable. X, in other words, x naught is a constant. And a constant means it is some number, some value that does not change throughout the process being discussed or throughout the problem or the experiment being discussed, right? It might look like a variable because it's a letter, but it's really a letter that is standing for a specific unchanging number. And we do want to get used to that, okay? So at the end of the day, so we're looking for the specific amount of work that's going to get done from this specific place to this specific place. We're looking at the end of the day for a specific amount of work as measured in joules. Our specific amount might be expressed in letters, not numbers. But our answer at the end of the day, even if it has letters, they better all be constants, such as x naught and k and stuff like that. Letters that are just standing for unchanging numbers that we happen not to have specified. Okay? So we're going to calculate that. So here we go. Sorry, we're going to calculate the work done from x naught to 0, or from x naught to 0 by a spring, which is exerting a Hooke's law force of kx. Excuse me. So we apply the definition of work, which is the integral from x naught to 0 of the dot product of force with displacement. Okay, so I'm applying that definition. Now, I'm noticing, first of all, I mean, I should have drawn a diagram. I neglected to draw a diagram, but this is the same diagram we're using over and over again from homework 1. I'm noticing that the force is pulling to the left, bringing the mass back toward equilibrium, which is over here. And the mass is being acted on by that force and by nothing else. It is displacing to the left. The force is pulling purely horizontally, and the displacement is purely horizontal, and both in the same direction. So in my first step, when I go to apply the concept of dot product, when I say that the dot product of the force vector with the displacement vector really equals the magnitude of one force times the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between them, I then realize, oh, the angle between them is 0 degrees. The cosine is 1. So I'm not ignoring the dot product. I'm not ignoring the vector symbols. I'm computing them and realizing, oh, they're quite straightforward in this example. Like there is no fancy cosine or fancy angle to deal with. There's no components to deal with. This dot product A dot product is designed to treat two vectors as though they are already quantities just sitting on the same number line. And these two vectors are just quantities that are already sitting on the same number line. They're both purely horizontally directed. So I have the integral of f times dx times 1, which is the integral of f times dx. So then I plug in, what is the force? The force exerted by a spring, the force exerted by a spring is negative kx. Right. And again, please remember, K is just a number. Really, in the homework example that this is all coming from, the number we're supposed to be picturing is 200 newtons per meter. But I'm leaving it as K because I'm saying everything that I'm learning here or figuring out for myself will be true and will apply no matter what the details of K happen to be. Right. So I'm leaving it general. It's general, but K is still a constant. Very important thing to get used to in higher level physics and math. All right, so I've got the integral from x naught to 0 of f dx times 1. So then I plug in the f. So I've got the integral from x naught to 0 of negative kx dx. That's the integral I'm doing. That is the definite integral. And it's from x naught to 0 because that's the direction that the thing is actually moving in. That's the direction that the force is acting in. So I'm integrating from a place to another place. Right? So now I've got to actually do this integral. Now it's time for calculus, right? Like I don't mean it to be big and bad and scary, but like we set up this integral because of the definition of work. Now it's time to actually do it. Let me remind you or tell you, and you might want to put this in your notes, a function is a box. You put a number in, you get a number out, right? Or it's a rule, it's a mapping, it's a relation. A function is. You put a number in, you get a number out. That's what a function is. So a function is something that takes in a number and produces a number. An operation is something that takes in a function and spits out a function, right? What's an example of an operation? Well, taking the derivative, differentiating, that's an operation. Or similarly, integrating, taking the integral, that's an operation. We don't integrate numbers and we don't differentiate numbers. We differentiate functions. And what we get when we differentiate or integrate functions, what we get is new functions. Okay, so at this step here where it says I need the integral with respect to dx of negative kx, I'm now going to do that integral, or you're going to do that integral, and what we're going to get is a new function. Then, if we want to get out a number ultimately and finish this problem, we're going to have to plug values into that function. Remember, a function takes in numbers and spits out numbers. A function of x takes in a value of x and spits out a new value of the function. Here, and in all integrals, we're integrating from a particular value of x to a different value of x. We're asking how much work is being done as we push from the value of x called x naught, which might be like 15 centimeters, all the way to the value of x known as 0, right? So we're going to integrate this function. You're going to give me a function as an answer to the integral of this. And then we're going to evaluate, meaning, okay, now we got a rule, we got a function. Now, what we're going to plug in the value, we're going to plug in the two possible values of x and subtract them to find out what the total effect of this function was. Why subtract? And why are we going to subtract in a backwards order? Like, why are we going to subtract the bottom value from the top? Because if I asked you, how tall have you gotten since January? How tall have you gotten in the last 2 months? What you would do is you would write out how tall you are right now. And underneath that, you would write out how tall you were at the beginning of January, and you would subtract, right? How tall you've gotten since January is your height now minus your height at the beginning of January. So the integral from here to there is the value of the function there minus the value of the function here, if that makes sense, right? I mean, you're calculating a difference. You're calculating an effect. So you subtract the earlier from the later. All right. So the first thing I'm going to ask you, and I'm going to pause now. I'm going to ask you in the direct chat, can you tell me the integral of the function negative kx? In other words, can you tell me the antiderivative of negative kx? In other words, can you do the power rule that we just did, please, backwards? Like right? Like we have a function here, negative kx. In other words, it's the number negative k, that's a number. That's like -7, except k is just written as k. Or it's like the number negative 200x. We have in effect here negative kx to the 1th power. I want you to come up with the function that if you took its derivative, you would get negative kx. I want you to do the power rule that we just did, but backwards. And in the direct chat, please, and I'll wait until I get a bunch in the direct chat. So I want the function that when you differentiate it, when you take its derivative, you get negative kx. Awesome, things are happening in the chat. Nice, direct chat person. And there's one person right now in the direct chat. So if you just put something in direct chat, I'm talking to you and you got it right. And that's very good. And I'm very proud and very happy. Like seriously, you nailed it. And and good. All right. Now there's other things happening in the direct chat. Now there's a bunch of happening in the direct chat. Awesome person who just went, okay, awesome. And now some of these are actually right and some are making more. No, person who just said, I'm not sure, LOL, you are right. Just for the record, the person who just said that he or she was not sure is correct. Just want you to know that. So good for you. And now I will say, person who put in, okay, so I'm going to keep, no, that's awesome. That's awesome. Awesome person who just wrote, awesome. This is so awkward. I know. I'm going to make it more awkward. If you have brown hair, 4 pairs of glasses, 3 boots, and a pants with ripped in them, then you're right. No, I'm just totally kidding. That's ridiculous. But yes, no, so a lot is happening in the direct chat. I'm going to be honest right now. I'm going to tell you some of the answers in the direct chat are right, and some of them are not, which, by the way, it means this is a class, right? It means it's worth it that we're together. If you were all wrong, we'd have a problem. If you were all right, it means I'm wasting your time, right? No, there's actually quite a mix of answers here, which does make it seem like this is a valuable thing to be discussing. So don't be ashamed or embarrassed if your answer is wrong, and do submit it in the portal for extra points for wrongness. Like, I'm dead serious. I will admit to you that some of your answers are not exactly right, but some of them are. And some of them are very clever. Oh, and I see what some of you people, okay. And some of you are making it a little bit harder on yourselves than it actually is. Okay, I'm going to wait for those 2 more answers because I don't want to, and then I'm going to address. Hold on, I'm just going to address a couple of things. I'm going to wait for like 2 more answers and then I'm going to go on. But, I know Zoom, I still prefer I shouldn't say real. Of course, I still prefer live classes to Zoom, but there's some things about Zoom. You can't do direct chat in a live class. Like, it's one thing, if you think about it, it's like one of the cooler things. So hold on one second. I will. Hold on. Okay. I think there's just enough. I am going to respond to everybody. Hang on once. Bear with me, please. I think, okay, I know this is like really inefficient, but I really kind of love this part. No, I think everybody who put something in direct chat, I think I've just responded to, for right or for wrong. And I'm really impressed. Like, again, this is a good mix of responses. It does. And I really appreciate the guts. Like I'm very impressed by the people who got it right, and I'm very happy, but I'm in a whole different way. I'm super impressed by the people that are willing to do this, even when they're not sure. But yes, there were some right answers, and hopefully whichever one you put, like a right answer or wrong, hopefully you just got some feedback from me. And if not, I apologize. It's an oversight. I think that's everybody. So all right, so I'm gonna and again, if you happen to have nailed calculus last semester or 2 semesters ago, like if you feel like you got this, that's good. I mean, and that will only make things easier for you in this class. But I would also urge you, if you think you're okay with the calculus mechanics that we're doing right now, then also don't tune out. Take it as an opportunity to now, since if you have your mechanics, your procedures straight, then relax that part of your brain and allow yourself to actually try to see how this is all related. Again, please, I know I oversay this, but I can't say enough to all of you. This whole idea of like, oh, I've done this before, or this whole idea of, oh, I already learned this, so now I'll go get lunch, is like so ridiculous. I mean, it's almost as ridiculous as this whole idea of science education, where we think that if we tell you something once, then you're supposed to get it and then get it right on the test. And then there's no excuses for you to have to hear it again. Like nobody gets anything the first time they hear it. Like nobody. They might get it to a certain level, but we always get it more and more each next time we do it and practice it. If that weren't true, I could not possibly find this interesting to talk about like 3 times a day, 30 years later, right? Like each time I get a new, deeper understanding of this. So it's okay if you think you're hearing it for maybe the second or third time. Like I assure you, that will only make you better at it, not more bored of it, if you have an open mind. Any hoodles, that's not a word. Okay. So anywho, this is what what I believe is, as many of you told me in the chat, we got negative kx as our function. The power rule said that when you want to take a derivative, you multiply the whole function by the power, and then you lower the power by 1. We want to do that in reverse, but literally in reverse. So we want to reverse each procedure, and we want to reverse the order in which we did the procedures, right? Like if I want to say go Dan backwards, right? If I want to say go Dan backwards, I don't say og nad. I don't just flip each word. I flip the whole thing. So I flip each word and I flip the order of the words. If I want to say go Dan backwards, I go nad og. If you understand what I'm saying, like you got to flip the right. So similarly here, if our old procedure was multiply the whole thing by the power, by the exponent, and then lower the power by 1, if we want to literally unwind all that, then we want to do the whole thing in reverse. We want to raise the power by 1 and then divide everything by that new power, right? Like that's what we want to do here. If we want to do an antiderivative, so we're going to raise, so the power is 1, we're going to raise it to 2, and then we're going to divide the whole thing by 2. So the function we get, as many of you told me, thank you, in the chat, the function we get is negative kx squared over 2. That's the function we get. That's the function. But we're not done because we're doing a definite integral. We didn't just ask in general, when you take the integral of this type of function, what type of function do you get? Like that's part of what we're asking, but we're specifically asking if you integrate from this value of x to this value of x, what value do you get at the end of the day? So we first integrate the function. We say, oh, well, when you're integrating a function that's negative kx, what you get is negative kx squared over 2. But then we're saying, okay, but now you asked me to look at that function or the continuous sum of products of that function from x naught, the value x equals x naught to the value 0. Let me even emphasize that by saying like the value of x there to the value of x there. That's what you're asking me? Okay, so now I'm going to plug in those values and subtract. And I'm going to plug in the final value and then subtract from that the result when I plug in the initial value, right? I know it looks like we're going backwards. It's always a little confusing to people. You integrate from here to there, and in order to evaluate, you plug in and subtract from there to here. But it's not a contradiction. Again, it's like saying, if I want to know how tall you got from then to now, I plug in your height now, and I subtract from that your height then, right? So that's what we're doing. We're plugging in we're evaluating, we're applying this function to the values of the independent variable. So we plug in 0 for x and subtract from that what happens when we plug in the number, the value x naught for x. Remember, x is a variable, x naught is a value, a particular but unspecified value of that variable. So we plug in, sorry, my chat is in the way of my shoot. Okay, so we plug in, right? And then you notice we got all these negative signs flying around. Like we're subtracting, but the whole thing is there's a negative, like there's this big bad negative sign before the whole thing because there was this big bad negative sign there because Hooke's law says that the spring always brings you toward equilibrium, right? So we got all these negatives. So in a negative times a negative is a positive. So what turns out, right? If you think about it, like we get, hello. Oh, wait, no, sorry, this is not, that's not, there we go. Now right. I mean, when we distribute, that's what you see what I'm trying to say. We've got this negative on the outside, so that when we distribute it, right, we get a double negative on the other term, so that becomes a positive. So that becomes just easier to write it as positive kx naught squared over 2 minus k0 squared over 2. In other words, what I'm saying is, if you notice, just because we have this negative that got distributed through the whole thing, and a negative times a negative is a positive, and then it's just, and then so what we're just realizing is whenever you want to get rid of a negative sign, if you want to multiply by -1, that's equivalent to reversing the order of subtraction. So whenever you have a negative out in front, you can always get rid of it. Whenever you have a negative out in front of an integral, you can always get rid of it by flipping the limits of integration, because the limits of integration are just telling you what order to do subtraction in. And a minus b is the same thing as negative b minus a, right? So I'm just, that rule that you might know from calculus, oh, if you flip the limits of integration, that multiplies by -1. It's just because the limits of integration are telling you to subtract. So I just did that here, right? I mean, I didn't apply the rule. I just discovered the rule here. So what I get in the end is, in the end of the day, I get like positive kx naught squared over 2 minus nothing, right? And kx naught is, x naught is a number in principle, just an unspecified number. So what I'm saying at the end of the day, so it says here, to get rid of a negative sign, we can always flip the limits of integration. Like that always works. If you understand why it happened here, then it always will apply. So in the end of the day, what we're saying is the work done by the Hooke's law spring in order to restore a mass from the value, from the position x equals x naught all the way to the position x equals 0, the work we get is 1/2 k x naught squared. That is a particular amount. Like if you plugged in 15 centimeters for x naught and you plugged in 200 for k, this would be a number, 100 times 225 centimeters. So 22.5 centijoules would be, if that makes sense, would be the answer here. So we could generalize this. I'm saying if x naught had been any value at all, whenever you want to know the work done by a spring to get from some position x back to 0, the work done by the spring is 1/2 kx squared. You may recognize this from high school or from last semester or something. Sure, it's a memorizer. You can take it to the bank as long as you know specifically what it means. It's not, it is the work done by a spring to restore a mass from position x back to equilibrium is 1/2 kx squared. Okay, pause for a second. Okay. So what? Good question. I mean, let me emphasize that is a result right there. Like what we just practiced, we just did our first application of integrating a force function in order to compute the work done by that force function. That's what we just did. Specifically, we just calculated the work done by a spring in order to restore a mass to equilibrium. So this is a general result. This is the work done by a spring. Like it's not a small thing. But so B, that's a B. But now I'm saying, okay, so what? Like who cares about work? Like, why do I care about work? What work is, again, triple equal sign, is the accumulated effect of a force as it acts through some measurable region of space. That's what work is. Why do I care about that? What's the consequence of work? In other words, what's the double equal sign lurking at the end of this road that made me care about the triple equal sign of work in the first place? Oh, good question. I'm glad I asked. Well, in order to answer that question, in order to see the consequence of work, let's go back to our elemental case, like our building block case, our simple, small, fundamental case. Let's imagine we have a force acting over a small but finite amount of displacement, small enough to hold the force constant. And let's assume that the force is not only simple and constant, but that it's directed along the same axis as the displacement itself, as is the case here for a spring. So let's assume that we got a small force, and let's even assume if we want, we got a bunch of forces doing that on some mass. A bunch of small but simple forces acting on some mass throughout some displacement. I want to see what the effect of all these, I want to see what the consequence of all these forces acting on a mass will be. In other words, I want to know what the net work done on a system is. So I'm using that sigma symbol again here. I'm once again using that sigma symbol to mean sum of, right? But I'm sort of using it in a more broad, general sense than I used it last week. I'm reminding us that the sum of all the forces acting on an object makes the object accelerate, right? Newton's second law, the sum of a bunch of forces acting on a mass accelerates that mass. So if I have a bunch of forces, so the sum of forces acting through a displacement on some object, I will then the sum of the work, the net. Okay, just so you know, should I say this? I literally just got a text message from a person at another college, someone that at another college just texted me and said, what's the difference between a force acting over an interval of space versus a force acting over an interval of time? Like that. And the answer is this, what we're doing here, but that just happened. That's a little weird. Okay. God, but why doesn't focus work on my phone? Why does my phone have ADHD? Okay. I'm looking at the net work done on a mass. So it says, look at the bottom line on this page. It has a big sigma symbol just because I'm trying to say net work, sum of all of the forces. I'm not getting into all that I equals 1 and all that stuff. It's not going to get that crazy, but I'm just saying, so we might as well use the word net here. But anyway, in fact, let's do that. This is unnecessarily confusing. Hold on a second. Okay, so if I want to know the net work done over a small interval of space, I realize that work is force times displacement, and net force, is ma. So I'm plugging in ma for F. That's all I'm trying to say right now is I'm just plugging in ma for F. So I get delta W approximately equals ma times delta X. But if we're assuming that the force doesn't change, then the acceleration doesn't change. So we can use our good old constant acceleration equations. Any of them, all of them, particularly one that's a little bit obscure that we derived at the end of that chapter in Physics 203. But we derived this one equation, so you may or may not remember it, but we did. It's this one equation, A equals V squared minus V naught squared over 2x. We derived that equation specifically for any kind of problem that did not make any reference to T and did not ask for any answer regarding T. It's the one equation. We just took a bunch of equations and we put them together algebraically to come up with the one equation that made no reference to time whatsoever. It was just a shortcut to save us from doing simultaneous equations. And that one equation is written right here in the middle of the page. A equals V squared minus V naught squared over 2 delta X. We used to just write it as 2x. Now I'm writing it as 2 delta X. It doesn't change anything. It's just I'm now being more clear and rigorous in specifying, reminding us that X is some small but finite difference between two positions. So I'm writing it as A equals V squared minus V naught squared over 2 delta X. It's just an old equation from kinematics. So I plug that in for the value of, and I want that one because exactly here we're looking at situations that make no reference to time. I mean, that's why it's funny that that text message just came in. The whole idea is we're looking at situations where we know the instantaneous speed over here at some position in space, and we're being asked to compute the instantaneous speed over here at some other position in space. We're looking at the effect of some force acting through space. That's what calls in to our minds this whole idea of work and energy, force through space. There's no reference to time in any of this discussion. So that's why I didn't just arbitrarily just think of any random equation. I thought of the equation that makes no reference to time. A equals V squared minus V naught squared over 2 delta x. So I plug that in for A, but it has a delta x in the denominator. I'm plugging it into this, into the top equation, to, you know, into this. Hold on. I'm just changing. So all this is the net. So we're looking at the net work done on some system. And when we plug, so the net work done is MA times delta X, but A is V squared minus V naught squared over 2 delta X. So then the delta X is cancel, and we end up having that delta, that a little bit of net work done is on a system is MV squared over 2 minus MV naught squared over 2. Right, that's what we're saying so far. Now, and that's a big deal. I want to make a big deal about it for the next 13 minutes. But I want to make such a big deal that let me first acknowledge that we just did a little bit of weird algebra just to derive a little result that supposedly applies to the small, simple case of a constant force acting over a small region of space. But forces obey superposition. That is, the whole equals the sum of its independent parts. That is to say, whatever a bunch of little forces do over a bunch of little displacements, if you add them all up, you get the total effect of what all the force does over all of that displacement. And if you take that to the limit where each little displacement is infinitesimally small, if you take that to the limit when delta X approaches 0, it's not going to change anything on that right side of the equation, because the right side of the equation doesn't have any delta X's in it anymore. They canceled out. Whatever's happening on the right side of this equation, whatever result we just got about V's and V naughts, they don't have any delta X's in them. So when we go to the limit, as delta X approaches 0, nothing is going to change that right side. Therefore, I'm going to say right now, before I turn the page, that we just basically analyzed the little brick and found out something that was true of that little brick. So I'm now going to say, well, if it's true of each individual little brick, if I make a whole big brick house out of all those bricks, it's going to be true of the whole brick house, because the brick house got nothing going on besides a bunch of bricks. So in less metaphorical language, I'm saying that we just discovered, it doesn't look like it much of a discovery, but it is. Yes, it is. We just discovered something that's true. Something that's true about speeds when you push something across a little displacement. I'm now saying if that's true across little displacements, it's going to be true across big displacements, because that doesn't matter how big the displacement is. The right side is telling us something about speeds. So I'm generalizing this result and saying that in general, no matter how big your displacement is, even if you go to the limit, in general, look in the middle of the page, the thing that's boxed, this thing, hello. I'm saying this right here says, in fact, let's make this really clear. I'm saying that if you have any system, any mass, M, and you do a net amount of work on that mass, like you have a bunch of forces acting together that all produce a net force, a net effect of force pushing in a certain direction. So that mass gets pushed in a certain direction throughout a certain space. What ends up happening is we change the 1/2 mv squared package of values of that thing from some old value 1/2 mv, some initial starting value 1/2 mv naught squared, to some final value 1/2 mv final squared. In other words, I'm saying, look what we just got. We got 1/2 mv squared minus 1/2 mv naught squared. I'm not saying that the 1/2 or the m or the v squared is supposed to make immediate sense. I'm just saying, notice, just like x minus x naught means displacement from x naught to x, like just like height now minus height before yields my difference in height over time, right? What this is saying is that when you do work on something, when you do work on a mass, you change very directly and very predictably and very precisely, you change some aspect of that mass, of that system. We might have thought when you push something through a distance, we change its velocity. And we do, but not in a straightforward, predictable numerical way. When I do 3 joules of work on a mass, I don't give the mass 3 units of velocity. First of all, the units of work and the units of velocity are not the same. If I do 3 joules of work, I can't give the mass 3 joules of velocity because velocity is not measured in joules. It's measured in meters per second. So it would be a very bizarre coincidence if by doing 3 joules of work on an object, you give it 3 meters per second of velocity. Like, why would that work? Well, maybe it would be nice, but that's not the case. When you do work on something, you do speed it up, but you speed it up in this funky way. When you do positive work on something, it turns out to see what numerical predictable effect you had on the motion of that object, that mass, that system, what you have to do is look at a whole package of measurable values. What this statement, W equals 1/2 mv squared minus 1/2 mv naught squared, is saying, it's saying that take our mass that's on our spring, okay? That mass, right before the spring starts working on it, it has a certain mass, 0.3 kilograms. Put that in my bag. I measure the mass and I put that in my bag. Then I look at its speed before the spring starts acting on it. The speed is 0. According to this equation, I take the 0, I square it, I multiply that square by the mass that I just remembered that it has, and I divide the whole thing by 2. Like, it's a weird procedure. It's not an obvious procedure. It's not anything that I would have thought of before. I'm only thinking of it now because the algebra seems to be spitting it out as some sort of important result. It's saying, if you want to see the effect of work on a system, take the speed of the system at the beginning, square it, multiply by half of its mass, put that whole package of measurements, put that in your mind, right? In this case, it would be 0, because at the beginning, the speed of the thing is 0. So I take like 1/2 the mass, and I multiply by this 0, which is the square of the speed. I take that whole number 0, and now I start working on the mass, and I do work on the mass in joules. And then I get to the end. I've pushed the mass 15 centimeters with a force force that was continuously changing. But I do this work on the mass for the 15 centimeters. I get to the end. Now I look at the mass, and it's really going fast. Now it's going like 3.787 meters per second. I don't say to myself, oh, I see the speed went up from 0 to 3.87 meters per second. I guess I did 3.87 joules of work. No. What I notice is, at the end, I take its speed when it is at the end of 3.87, I square that, I multiply by its mass, 0.3 kilograms, I divide the whole thing by 2, and I compare that number to the original number of 1/2 mass, speed squared, and I notice, oh my God, the 1/2 mass square speed package seems to have changed by the exact same number of the joules of work that I did on it. And I look closer and I'm like, oh, wait, that actually kind of makes sense, because joules are newtons of force times meters of displacement. 1 joule of work is 1 newton of force times a meter of displacement, and a newton of force is a kilogram times meter per second squared of acceleration, right? Like F net equals ma. So a newton is a kilogram times a meter per second squared. I do that through displacement, so it's kilograms times meter per second squared times meters. Well, that's the same units as mass, kilogram, times meters squared divided by seconds squared. Both sides of this equation are in kilograms times meters per second squared times meters, right? And it turns out, in other words, if I look at the whole package of something's half of its mass times its square speed, I look at that whole package as a bundle of joules, whenever I do work on that package, if I will give I will increase its number of joules by precisely the amount of joules of work I did. Okay, and again, why 1/2 mass square speed? Because that's what the algebra says. I mean, because that's what works. But so from here on in, therefore, we give a name. Like, it's very awkward for me to keep saying 1/2 the mass, the square speed. So we give a name to that whole package. That whole package of parameters or of descriptive features of a system, that whole package we call the kinetic energy. From here on in, we call it the kinetic energy of a system. And we say from here on in that when you do work on a system, what you do is you change the system's kinetic energy. What is kinetic energy? It's the ability to do work. Wait, what is work? It's the transfer of energy. Wait, what? Is that a circle? Yes and no. Yes and no. Work is force through a displacement. When you do work on something, you push it or pull it through space. What I'm saying now is that when you do that to something, when you push or pull something through space, what you do is you change a measurable description of that system. You change its 1/2 mass speed squared by the exact amount of work that you did. When you do work on a system, you change its kinetic energy. More specifically, if I do 5 joules of work on you, if I do positive 5 joules of work on you, then I literally give you 5 joules of kinetic energy. Your kinetic energy will go up by 5 joules. Mine will go down by 5 joules. So I'm literally transferring kinetic energy to you when I do work. When I do positive work on you, I transfer kinetic energy from me to you. And then you could very easily say, well, what is kinetic energy? And I could say, well, it's 1/2 mv squared. And you could very easily say, fine, that's what it is mathematically. But like, what does it mean? What does it mean that I have kinetic energy? Good question, good question. And what I would say is, what it means that you have kinetic energy is that you have the ability to do this to somebody else now. I'm saying work is the transfer of energy, and energy is the ability to do work. And if you think that is a circle, you are correct. But it's not a meaningless circle because it's just like this. Literally, it's just like money. It's like money. I want money. Why do I want money? Because I want the ability to spend, right? I want money so that I can engage in a transaction and give it to you in exchange for something else of equal value that has a different form that I want. Like I want to buy your Pokemon cards. Energy and work is the same thing. Work is the transaction when we pass energy from one system to another. Energy is the ability to perform that transaction. The reason it's not a meaningless circle is that sometimes you have a whole bunch of energy in one form, and if you transfer to some other system, what you might get in exchange is energy of a different form that you need more. Like energy can be kinetic, or it could also be, as we will discuss next time, potential, or it could be thermal, or something else. So work is the transfer, i.e. the transaction, the act of passing it, the change from one system to another, and energy is the commodity itself, the ability to engage in that transaction. So that's where we end today. I'll pause for a second if there are any questions, but it does have to be quick because I have another class right after this electronically. But you've been great. In the homework you saw like extended, blah, but you still get more points. Blah. So yes, have a good day, Jose. Thank you. Right, exactly. Have a good day.
Hi, Professor. Thank you.
Thank you, Carolyn. Good job. Awesome. Everybody, great job. And yes, have a great job. Have a great day. Okay, cool. Yes, have a good day. And I still have to respond to your message, direct chat person. Sorry, I owe you an email, but yes, thank you guys. Okay, and I'm going to go in a second because I have this other class now. Yikers Island. Oh, yes. Wait, hold on. Yes. Wait, great question, direct chat person. Yes, you can still always get, yes, until I remove the portal or something, as long as the portal's up, eventually you can get all the points. You just might not get them as quick as someone else. And I don't want you to fall behind for your own sake, but yes, director, you still can get all the points. Yes. Wait, just tell me if you got that. Like, okay, cool, awesome. Okay, awesome. Okay. And great. Oh, and you're the only one left. Wait, I got to turn off the recording.